I think you do.
Shall we, Dan, do you want to start with the presentation, or we'll go with that?
Okay,
And
I'll try and do this very quickly. Do you still hear me?
I do.
Will you go into presentation mode, please? All right, can I advance it, or I need to ask you to advance it?
I'll advance it.
Okay, next slide, please. So yeah, very briefly, Sophion Bioscience is from a small country called Denmark. You might not know it, it's a kingdom, or actually a queendom, but you might know the Little Mermaid, the fairy tale writer H.C. Andersen, and the world's largest container carrier Maersk Line. And then you might also know that we have Greenland. Next slide, please. So we are founded in Copenhagen, Denmark, and we also have offices and labs both at Boston and Tokyo. Next slide, please. So we have been instrumental in developing automation of patch clamp technology. This Nobel Prize winning technology that first Hodgkin and Huxley invented or described by means of ion channels back in the 40s and 50s, and later Neher and Zachman invented the patch clamp technology. We turned that into an industrialized product with the first Apache back in 2001, and then we've developed a lot of things, with the latest major event being our 384 format APC called Qube, which has also adaptive protocols where you can interrogate every single cell. Even though you're recording in parallel, you can interrogate every single cell by means of its own biophysical characteristics. That's a very strong feature to tighten up the data spread from biological variation. Next slide, please. So we cover the whole range from basic research all the way to drug screening by means of having two instrument lines. The black one is a Qube that I'm talking about today, and the white one is Qube-2, which is a similar instrumentation that is slightly more flexible than the Qube and has a capacity of 16 or 48 parallel recordings. Next slide, please. So by covering the whole drug discovery cascade from the very beginning, we have the ambition to actually replace the otherwise normal secondary screen or confirmatory screen or whatever you like to call it, because normally the first step is done by fluorescence means recording the ion channels, and since that is an indirect measure, for instance the flipper or other good instruments, because that's an indirect measure of the activity of the ion channel, you will have to use electrophysiology later on to confirm the hits that you found. But starting off with a real electrophysiology, you can omit the secondary screen and thereby obtaining the leads faster. Next slide, please. We have also, I mean, normally we use cell lines and drug discovery on these instruments, but we have also looked into whether they can do more, should we say, sophisticated stuff. And in this case, I'd like to show you some data from recording in 384 parallel recordings from induced pluripotent stem cells derived neurological disease models. So next slide, please. Together with brain Excel, we have had the chance to look into these iPSC derived motor neurons. It's a difficult cell type to handle, and actually some of the more challenging step was to actually handling the cells, so covering the step from the incubator onto the instrument, because we need to lift off the cells, bring them into suspension, and then the apparatus takes on from there on and bring them into the recording plate. But nevertheless, we managed to, in the best recordings, get up to 60% success rate, and success rate here is defined as a membrane resistance better than 200 megohms. We express the tightness of the seal between the cell and the recording substrate in ohmic resistance, and 200 megohms is good. We normally talk about gigaseals, but in this case, we set the limit at 200 megohms to obtain the recording. And as you can see, we got a inward reflection that is normally carried by a sodium current, and we also got some outward reflections, and we even could record some current clamps from this. Next slide, please. So we dug deeper into this, trying to characterize what it was, because having a somewhat native cells, you can have a whole orchestra of ion channels expressed in it. So we made use of various well-defined pharmacological agents, for instance using tetrodotoxin on the lower left panel to show you that the currents that has this sort of V-shaped characteristics, people in the field will know this as an IV curve. That IV curve could be totally blocked by adding 1 micromole of tetrodotoxin, indicating very strongly that there are voltage-gated sodium channels of the, should we say, grain type in this population. Also, the outward current was carried by voltage-gated potassium current, as demonstrated by means of their sensitivity to 30 micromolar TEA and 4 millimolar 4-aminopyridine. So with these agents, we could say that more or less all of the cells were expressing sodium and potassium currents, respectively 85 and 98%. Next slide, please. We also looked into some ligand-gated responses, like gamma-aminobutyric acid, or GABA, to see if we could find any such channels expressed in those cells. And in 45% of the population, we actually saw a response to adding GABA. You see here 2 panels. That's because the instrument can apply the ligand in 2 different modes, actually more different modes, but here shown as 2 different modes. We have what we call standard, is a somewhat slow application before we start the washout. And in the right-hand panel, you can see we can also do the ligand application in a very, very brief, with a very brief exposure of the ligand, namely less than 1 second exposure of the ligand before we do the washout. That is very useful if you're dealing with desensitizing ligand-gated ion channels, because thereby you can omit the desensitization and you can have the cell as its own control, because you can stimulate it over and over again. Next slide, please. So we looked into what about the expression versus the day in vitro, and we found a sweet spot around about 11 days where we have high success rate and also a decent expression level. Next slide, please. And most interestingly, we had access to a different patient population. With one example is the spinal muscular atrophy patients, and we could, on the same instrument with cells from both controlled, diseased patients, and also diseased cells that had been rescued by means of adding a compound called SMC3, see that we could rescue this extra expression of voltage-gated sodium channel. That totally aligns with the literature data that you can see in the lower left corner. Next slide, please. Also, another type of disease cells from amyotrophic lateral sclerosis patients, we could see that we could run control cells. We could run cells that carried the ALS causing mutation D90A, as well as a rescued, a CRISPR rescued population of those cells from patients, bringing them back to the control level in a significant. So we saw these significant differences in, again, the expression level of voltage-gated sodium channel. Very, very nicely that you can run that on the same instrument, having a lot of data because of the 384 format, and doing everything else in parallel. Next slide, please. With that, I'd just like to apologize for the delay in getting my voice on, but I hope you got some data out of this, even though it was a pretty speedy version of it. I'm happy to take any questions you might have.
Oh, thank you very much, Mads.
I think I caught up almost.
I have a few questions left over from Medisense here, but I also, in the interest of sticking to our promise of making this an hour, what I'm going to do here, Dan, unless you feel otherwise, is say thank you everybody for attending. We'll take the open questions and we'll forward them to the presenters, and hopefully that can create a good dialogue. Again, on behalf of LRIG, thank you very much for attending.
You're welcome.
And thanks once again to all of the presenters.